स्टार्ट करते हैं। मैं वेट करता हूँ और फिर लोग ज्वाइन करने को। Good afternoon. Let us wait for a couple of minutes just to ensure the other participants are also joining us today. Okay, let me start. I hope a few more participants are going to just join us. Yeah. So let me just recap on what we discussed in the previous session. That is, we had discussed on the basis of dispersion and transport and dispersion of CBR and pollutants if they are getting released, and based on which the modeling of these releases are actually constructed. So yesterday I have taken you through the basis of atmospheric transport and dispersion, where I have discussed the various aspects that actually govern the dispersion of transport and dispersion, especially the stability classes, how they are defined, how the lapse rate is used to define the stability categories, and how dispersion is going to be affected by different stability wind stability classes. And so this was what we discussed, and we also discussed what are all the models that are available, modeling domains that are available to model these dispersion of CBR and pollutants. Especially I discussed on the tools with respect to CFD, that is computational fluid dynamics. Then we discussed also the Gaussian plume method, and we also discussed about the particle Lagrangian puff and particle methods, and also chemical dispersion techniques. So these are the techniques I briefly discussed yesterday, and today let us move on to the next part of the discussion. If you remember this slide which I was mentioning yesterday, that the green ones is what the outcome, that is where the target is. Either in the preparedness phase, we need the dispersion modeling to prepare ourselves effectively for prevention and preparedness, and as well as the modeling of dispersion. Dispersion modeling is going to help us while in the management of an ongoing response. So these are the two major outcomes that we're looking at, and how these can how the modeling is structured. I was discussing about the release scenarios, meteorological conditions, which actually help us identifying the source term. What is the source term? That is the CBR and pollutants that is available for release or that is getting released, and the characteristics of these releases, the time of release, and in what medium, in what condition they are getting released is what is going to be dictated by the atmospheric meteorological conditions. And then you, based on these two, you evaluate the likely consequences. You do an exposure assessment. If it is a radiological emergency, then you try to find out the dose. What is the likely dose, or what is the dose that people have received, or they are likely to receive, and accordingly you either plan for the preparedness or use it during the response. So likewise, this is how it is structured. Okay. So we dealt with the basics of what are these fundamentals of these models, and today I will take you through the I will take you through the applications, okay, of these models. Okay. So yesterday, if you remember, I discussed on the three basic four basic models: the computational fluid dynamics, Gaussian plume, Lagrangian puff and particulate models, and chemical transport models. And I also discussed about each of these techniques, how they are useful, what is their merits, what are their demerits, and I was explaining you that the CFD model is going to be used when there is going to be a domain where you are supposed to assess the release conditions in a around a small area where the release conditions or the dispersion is actually dictated by the local geometries, or basically buildings, the complexities involved in that. So where those kind of details are important, which are actually influencing the dispersion, then you use a computational fluid dynamic model. And I've also told you the computational fluid dynamic model will be a computationally intensive one, but so accordingly, based on your need, you choose between these four models, whichever is applicable. Okay. So I'm going to give you a few examples of how these models are used. On your the first one, you see concentration distribution of a chemical predicted by Gaussian plume model for one case of field experiment. Okay, so I have taken these examples from one of the latest publications. You can actually, I've quoted the publication here for your reference, so you can go through this publication if you want, so that you can even you will be able to understand by your self reading. So you can even appreciate better when you later after the class, if you want to get in the depth of these models and how they are applied. So I specifically chose a very recent paper where studies have been done with all of these models, and so that you are able to connect to these simulations, to these studies. So here you see a Gaussian plume model where the chemical dispersion is just model, and you can see the Gaussian plume model gives a very gross estimate of from point source how it is getting distributed, probably in a unidirectional way. Okay. So here, as I said, there are a lot of assumptions that we take in a Gaussian plume model where the conditions are not much changing, and there is so here the assumptions are limited in the sense that it limits the model's capability to predict the dynamic conditions. Okay, so where if you want to only get such idea, so you generally use a Gaussian plume model, which is very computationally not intensive. It is easy to solve, and so that primary idea about how long it is going to how long a dispersion is going to happen, and what is the likely magnitude of the concentrations at various distances. If you want to just to arrive at these conclusions, arrive at these understandings, so you use such models. Okay, so later you can see on the middle one, that is the plume. Basically, this is a Lagrangian particulate model used to this is basically you can relate to the Wuhan seafood market. So they have tried to see that if a leak would have come from a market based on the local conditions, based on the local buildings, how these could have come outside the spread of these, across the domain. So they have tried to simulate that. Okay, and you can also see SF6 release and its prediction using a Lagrangian puff model. Okay, so this is a Lagrangian particulate model and Lagrangian puff model. Lagrangian puff model is little limited. Lagrangian particulate model is little more versatile in the sense that it can accommodate the release patches, final release patches. So then you also have one of the studies that based for Fukushima release condition, the atmospheric transport of radionuclide, iodine 131, okay, particulate released during Fukushima accident during using a chemical transport model. I was mentioning about the Polaris 3D model. So such model was used. You can see this is the Fukushima release source, and how it is getting dispersed across the Pacific. And how it is getting distributed due to the various weather conditions and across the time of release. It is not a one day 1 hour 1 day release. There were multiple accidents, multiple release conditions. So all of this put together, you have to have a weather prediction for all across all these days. And based on those weather predictions, whether windrows, then you make a dispersion of these radionuclides, and you come to arrive an estimate of what how it basically could have dispersed, and what is the likely concentration that could be available at various locations of interest. Okay, so such models. So these are, I've just specifically picked each one of the Lagrangian, Gaussian plume, and the CFD sort of analysis for each of these examples. So this is how you either use it for during an emergency, or if you are planning for any facility to set up a facility and to understand what is the likely hazard that what is the likely consequence that is going to be there for the particular hazard that the facility has. So you can use such models and estimate the risk due to the hazard. So now let's move to a decision support system. Okay. So what are the requirements? So fundamentally, let us see what are the requirements for a decision support system is. Okay. So it should have an online meteorological data from site-specific weather stations. Okay. So decision support system is what we talk about, like a tool that helps us in making decisions while an ongoing emergency is there. Okay. So for that, we need to have certain characteristics which is going to help us, which is appropriate, which is going to be realistic, so that can guide us in taking decisions. Okay. So one is you need to have a good online source of meteorological data from various sources, either from weather stations, and work on either pre-identified source term or release rates estimated from actual environment measurement. See, as I said, the source term is one of the important parameter that is necessary to actually this itself. I will discuss specifically on the source term in the coming slide. This itself is a huge important area that mostly larger uncertainty in all of these models is actually with the source term estimation. Of course, weather is also weather prediction is also a major thing, but source term has its own challenges. Then data on topographs, demographs, etc., which will give us which is needed for site specific or location specific, for accident specific decisions, and communication during emergency situations arising from natural events such as flooding, tsunami, cyclone, earthquake. So you should have a robust communication at these conditions, because to have a functional DSS is important. Just not enough that you have a DSS or you had a DSS. Okay, to have a functional DSS at this at this likely conditions, likely disaster conditions is very important to, at the end of the day, it should survive these disaster conditions, and it should be functional during these conditions. And the user-friendly iterative GIS system, geographical information system, which is again a critical parameter, and amenability to interface access with other external relevant government agencies, preferably through standalone web pages. Okay, so whatever system you are using, it should have the characteristics to get interfaced or access other relevant data or portals where your data or your predictions or your outcome can be shared as necessary for other responding agencies, not just you, not the one who is running the DSS or making the decisions for the DSS. It is most likely that the outcomes of the DSS will be used for used by various other agencies to execute their own support roles during an ongoing emergency. Okay, so these are some of the important requirements or the conditions that a DSS needs. So let me take you through a typical scheme. Okay, comes one by one. I didn't design it this way, but anyway. So you see there is an input domain, there is going to be a processing domain, and there's going to be an output domain. The very primitive structure of any tool. Okay. So when you talk about inputs, you talk about first weather prediction. Okay. I've discussed this slide in our earlier, not in detail, but I have discussed in our previous, part of our course. So you need first the weather prediction models, and you need the source term models. Okay. So these both can come from different simulations, weather predictions from WRS simulations, and source term coming from two different things. Source term itself either can come from accident conditions or whatever the facility conditions, which can be estimated from the likely condition or the predicted conditions for currently the facility is in. So each of the postulated accidents in any facility, okay, for example, nuclear power plant, there are many postulated accidents, okay, accidents are postulated, and defenses in defense in depth are provided for each of these postulated accidents, and over and above you have the emergency preparedness and response domain, that is level 5 defense in depth, to cater to any eventualities of any failures in the earlier defense in depth. And each of the postulated conditions you can identify source term for each of these postulated conditions. Okay, so example. So there are many, for example, there are five possible conditions a release can happen. Okay, scenarios a release can happen from an entity. Of these scenarios will have a different source term based on the kind of failures, kind of accident progression, the kind of safety system, the kind of safety system or the level of success rate of the safety systems. Okay, so the timing of these failures and the time available for release. Okay, all of this thing will be different for different postulated conditions, and each of these conditions can have a different source term. That is the amount of radionuclide available and their characteristics. What are the type of radionuclides that are likely to get released? All of this could be different for different accident conditions. So this is one source term you can use, okay, to start your decision making. And later, once you have the release have happened, you can also derive the source term from field environmental radiation monitors that are specially designed to estimate the source terms, okay, based on which you actually can do a dose projection. What are the likely dose that the public are getting or will be getting if there is no protection being taken? And if I take protections, what are the likely protections that would be necessary? Because the level of protection that you are going to implement during an emergency will finally be based on the level or the magnitude of the consequence. So the magnitude of consequence is important to decide on what is the level of intervention I need to make in the public life, because the whole of the perspective, you understand that it is all about doing more good than harming during any emergency response. Okay. So these are the input conditions that is necessary, and you process it using these models, the various models we discussed. Either you use a Lagrangian particulate model, the plume dispersions in this domain. You use either of these models. You use a Gaussian plume, you use a Lagrangian particulate model, you use a Lagrangian puff model, or you have a CFD model, and next you kind of get the dispersion and the concentrations distributed, and you also need to have these data processed across a effective GIS system, which would also give you that what are the various data, what the area that are getting affected by these by these releases, and what is the characteristics of that area, what is the village population centers, roads, what are the likely facilities available in those areas. So what are the timelines available for me to implement the protective actions? Do I need, how many, public primary health centers are there? So all of this data is going to be necessary for me to make any further decisions. Okay. So these are the two important central parameters I need. And of course, as an output, I will have the area that are affected during an emergency due to the release, and the projected dose or the projected consequences, and the system will also have to give me the best choice of protective actions. Okay, as I was telling, there is a strategy you need to frame. In this, after the learning of Fukushima, it is important to choose the right protective action. Okay, it is not right to implement all the protective actions individually. You need to choose a protective action by collectively looking at all the possible pathways and assessing each of the pathways, which is the main contributor, which pathway is mainly contributing, and what are the actions that is required to target this specific pathway. And you can add a kind of one or two more protective actions to that particular protective action if it is not doing more harm. Okay, so such decisions have to be made. That is the protective action decision. Okay, this is what is more important. So these are the likely output I need from a decision support system. Okay, so this is how I structure a decision support system. And I will again go through the source term part, which I said is an important part. The source term describes the type, amount, and physical parameters of the released hazard substance involved in the release. Example, the temperature, pressure, release time, and state of the substance. Okay, whether aerosol, whether it's volatile substance. And the source term estimation forms the basis for the dose estimation during nuclear emergencies and countermeasures to be taken. Prompt, realistic estimation during emergency is needed to ensure timely protective actions and timely implementation of protective actions. And a source term can be, as I said, it can be obtained from two ways. That is a forward calculation. That is a forward calculation. I mean that you know the condition of the plant, current condition of the plant, irrespective of measuring what is released. Rather, you estimate for this particular plant condition based on your own analysis, based on all the postulations you had made, or based on understanding of the various stages of the accident progression, at what time the accident started, and what was the timeline for the next level of degradation, what was the timeline for the safety system, how much, to what extent the safety system has functioned, what was the effectiveness of the safety system, and what was the time that was available before the release. So all of this condition you put together and you estimate a source term. Okay, this is the source term that could be there for this particular condition. Okay, so that is one way of estimating the source term. The other way of estimating the source term is to have a reverse inverse calculation. That is, you use environmental monitors, okay, to estimate the source term. So these are the two methods you estimate a source term, and this is how you can use this source term as part of your decision support system. Okay, and I briefly discussed about the forward calculation. The reverse calculation would be like this. You will have a release coming from here, and there are various measurements placed in different ways. I will show it up in the lower part will show how these measurements, how these monitors can be placed strategically, and you use the information from this, from this monitors, and you see, you basically it is like you give a unit release. Unit release of any radionuclides, and you see what is the likely dispersion, likely dilution and dispersion at a given targeted place based on the current weather pattern, and you estimate the actual release. So this is how the inverse method you use to calculate the source term. So you see, for example, this is one of our NPPs. So this is how the monitors are actually placed around the NPP site. So then there are many strategies you can place the monitors, so that this is a center line, and you can have each sector, for each of the sector you can have two different monitors this way. Okay, one close by and the other, then either you can have alternate sectors, that is one here in one sector, and at a larger distance in the other sector, and the closer distance in the alternate sector. So you can have such strategic monitors placed around the facility. And this is one of the example of a monitor that is kept in in and around a nuclear power plant that is actually designed, that is actually meant to see the estimate this reverse source term. Okay, so what are the challenges in this inverse source term? Okay, this inverse source term, as I said, as estimation of the source term itself is a challenge. Okay, even now you see the Fukushima source term were refined until 2020. Okay, based on lot of data, improvements in data, the improvements in treatment of uncertainties. So all of this put together, the Fukushima, the amount that actually released from Fukushima was estimated, and revised estimated were released until 2020. Okay, and there's still scope for refinement, which may not lead to better results, but still, what I would want to say is that the source term estimation is a critical area, and it has its own challenges. Okay, so there are large errors possible, and the reverse method cannot provide source term before an actual release, because you need to have source term, sometimes before even a release, to actually understand what immediately and what level of protective actions I need to implement in advance, that whenever there is an imminent release is going to happen, but you have time to do precautionary actions, and what level of actions you need to take. Again, your source term is necessary, and in that case, a source term before an actual release is important. And the recent reviews have suggested that unknown accidental release rates is the largest uncertain factor. Okay, in all of this, emergency management business, the release rate. Okay, because you never know what is the kind of failure. See, for example, we have a containment designed to retain or contain the radionuclides in nuclear power plants, and this is supposed to sustain these. The failure of this actually in design is practically eliminated, but still you consider emergencies are always to be planned for conditions that are not envisaged in design. So if you assume a failure of a containment, the failure would be very different. It depends on what kind of failure, how much the area of the failure. There could be small leaks in some penetrations, and area of the leak, area of the failure is going to dictate the release rates, okay, and what is the condition inside the facility, that is the pressure inside the facility is again going to dictate my release rate, okay. So such things is one of the very important parameter that holds a large amount of uncertainty. Okay, so new innovative methods to reduce uncertainties in emissions and accumulated errors during dispersion by combination numerical methods and monitoring data. By combining numerical methods and monitoring data, new innovative methods, for example, I would say they are using Bayesian belief networks to treat uncertainties. Probably you can also use, people have started working on using artificial networks to reduce these uncertainties in various parameters. Okay, so eventually you are going to measure, you are going to have some data, the measurement data, and you are going to have some idea about what what is the likely weather condition by that time, because weather itself is having going to be having a huge level of uncertainty. So you will have data, okay, but those data are not sufficient and they carry a lot of uncertainty. So treating this uncertainty is the challenge, and innovative methods are being arrived at to reduce these uncertainties and its influence on the outcome. Okay. So weather forecast is the next part. We saw the source term part. The weather forecast is the next part. And you see, you use a WRF simulation. You create a domain across your area of interest, and you can make nested domains. And you create you do a WRF simulations, and you get the various weather parameters, the directions, wind velocity, and changing wind directions, and all of this, you rainfall, if at all, if it is there at that time, and how it is going to, how you can also include the precipitation, and you consider a release from this point, and for such a weather condition, you can see, the if a release is going to happen at that time from this location, okay, from this location, and how the dispersion is going to happen. Okay, so this will give you the likely area, okay, and the area of focus, okay, and immediately how many villages or how many locations you need to implement protective actions. Okay, so it will give the complete dispersion pattern for a changing weather conditions. Okay, so this is basically a WRF simulation run across Lagrangian particulate model. Okay, and then how you get a dispersion of the radionuclides for a given weather pattern. Okay, so then you need to have the dose projection models. Okay, so before that, just say, okay, this is the dispersion and this is the concentration, let us say. Okay, so this is the concentration of the radionuclides you can see, and you can also refer one of the reference papers which I have quoted here, Raja Shekhar et al. From our own Indira Gandhi Center for Atomic Research. So they have done a very good amount of studies on this. They have developed a nice systems for these applications. And you have dose projection and countermeasure modules, which is necessary to actually estimate what is the likely consequence one would get. And you can first estimate, this is the D1, that is the projected dose. In the absence of any protective actions, you don't implement any protective actions. Without any protective actions, what is the likely dose, and then the time. Okay, you see, and then you will also have to estimate, if you implement a protective action, how the doses are going to be and how much dose you're going to avoid. And at the end of the day, when at the end of the day, when you're removing a protective action, and what is the likely dose, that is we call as residual dose. Okay, what is the residual dose will be there after removing a protective actions, because at the end of the day, the residual dose is the one that will guide us to make decisions on terminating an emergency, on optimizing our protective actions while when we are implementing the protective actions. So this residual dose, as I have discussed, which we call as a reference level, okay, is the one is very important. So the tool needs to have these capabilities. Okay, one I said source term. The second I said weather predictions and dispersions, and the third is the dose projections under countermeasure module. Okay, so these are the modules that I need. And other most important module is the geographical information system module, okay, which gives me that what are the villages details. See, I'm not sure you can. So you see, this is one of the system where the GIS information is made available, and each villages, each village will have what is the population in each of these villages, what are the likely what are the shelter facilities available, what are the close by road networks, and all of the details would be necessary for me to make decisions. Okay, so such a system, site specific GIS using topo sheets and satellite images is necessary. Land use data and details such as villages, hospitals, schools, industries, bus stops, railway station, everything will be available, can be made available through this GIS system. And atmospheric concentration deposition and radiological dose across over this data will give me the kind of protective actions that I need to take in each of these areas. Okay, so I have each of the villages, what village, what is the dose that is going to be in the villages. So accordingly, I can choose my protective action. I can plan a protective action strategy for each of these locations depending upon my decision support system, depending upon the outcome of the decision support system. The summary, the dispersion modeling plays an important and increasing role in emergency planning and response to CBR and accidents, can contribute to effective risk preparedness, prevention, evidence-based policy making and emergency response to airborne CBR and pollutants. Effective use of models and tools to support decision making is the key. Using these tools effectively, the understanding of the merits and demerits of the tools is going to be a key at this moment as we progress, as like in any other scientific domain, as we progress in better in improving our understanding and in improving our capability to do modeling and estimations. As of now, it is utmost important to understand and use these tools very effectively, and that will hold the key for an effective preparedness, prevention, and management of any CBR and disasters. Okay, so that's the summary. I would say conclude. I would say I'll conclude the lecture at this juncture on the dispersion and decision support system topic. And for the next few minutes, I will take you through another important topic, which I would like to share with you how the regulatory oversight is an important tool. Since I represent the Atomic Energy Regulatory Board, I would like to share how a regulatory oversight, what is the role of a regulatory oversight in the disaster management, and how it is being done. Okay, how the regulatory oversight, whatever the mandate a regulator has, how it is being done. I will try to take you through that. So just give me a moment. By then I'll switch the presentation by that time. Okay. So I would discuss a few major, key areas, the regulatory documents, the oversight for emergency preparedness, and emergency exercise methodologies in specific, and challenges in post-accident management. Okay, so first, I would keep early phase decision making and response as my, the major point. Okay, because the characteristics of overall emergency management will actually be dictated by the actions that we take in the early phase of an emergency. Okay, so the actions, the choice we make during the early phase will dictate the nature or the outcome for the subsequent phases of an emergency. Okay, so in that context, I would like to discuss a few cornerstones. That is, the first is that you need to have a technical basis. The second is that you need to have a policy and regulatory framework. The third is the response framework and the institutional framework that you put in place for an effective response that is conducive to early phase decision making and response, that is responsive to early phase decision making and response, and the plans and procedures that you have in place, and your preparedness in issuing public communications, handling public anxiety, handling, informing public during an emergency what is to be done, keeping them well informed is a critical cornerstone. And the exercise program as part of preparedness. Okay, what sort of exercise program you have, because this is the only one program in disaster management that allows you to test yourself, because disasters are not to be occurring, and for any system, for normally other system, you will have opportunities to test yourself, opportunity to see whether your framework functions, whatever preparedness you have, whatever functional aspects you have are doing their best. But in emergency, in disaster, that is not going to be the case. The exercise program is the one that is very critical, that is going to give you a feedback. That's going to give you a feedback on the capabilities of your system, on the readiness of your system. So it's an important cornerstone. And the oversight of emergency preparedness is also an important cornerstone. Okay, so I'm going to discuss on a few couple of things. That is, I will specifically discuss on the oversight and the exercise program that are being put in place. Okay, and these two, and then of course the regulatory requirements and guidance. Okay, so these are the three cornerstones that I'm going to discuss in the next couple of probably 15-20 minutes. Okay, so to drive a point, how these are important cornerstone in the overall emergency management. Okay, so the responsibilities of AERB, since I represent AERB, so as a regulator, AERB, what AERB does as part of disaster management, that is as part of emergency preparedness response, that is to establish regulations and guidelines which actually specifies the principles, requirements, and associated guidelines for emergency preparedness and response. So one of the important job is to specify the requirements and also give the enabling guidance through which compliance to these requirements can be done by the response agencies, and to ensure and verify that arrangements for preparedness response of the licensee are adequately done. So AERB can only oversee the arrangements of the licensee, as far as AERB is concerned, and the arrangements and the oversight of other agencies like district responses are and will be taken care by respective agency, that is NDMA and state authorities and NDMA. And during an emergency, what AERB does is to keep himself informed or apprised of the ongoing emergency at the facility, okay, and review of response actions by the licensee, and inform public and other government agencies as and when necessary. The information what AERB gives during an emergency is not a part of the response function, that and it will not interfere or contradict or undermine the public informations given by the local authorities during an emergency that's targeted to achieving certain protective actions for public. Okay, so the information given by AERB will be based on the independent assessment of the emergency actions, and to keep public trust or to keep public confidence that the actions taken are appropriate or not appropriate. So our job is to ensure that. Okay. So the regulatory documents, if you see, the regulatory documents are now, which I've already discussed in the previous, part of the earlier part of the sections. I'll just quickly go through this. We have now a structure where you have one safety code, that is a AERB safety code on management of nuclear and radiological emergencies, that is AERB NRF SE NRE, which specifies the safety requirements. And there are a host of set of guidance and guidelines documents that supports the response agencies, the licensees and the response agencies to ensure compliance to these requirements. And we are also, these guidelines, our guidance documents are now being restructured in a new RegDoc development series with specific focus, one for nuclear facilities, radiation facilities, and emergencies during transports. Okay, so these are currently being consolidated and updated. These guidelines are currently being consolidated and updated, and these are at advanced stages of preparation and publication. Probably in the coming years, you would be able to see these guidelines, the new revised, updated guidelines also coming out. Okay, so the new code, basically the SE NRE was published in 2022. So that's a safety code that incorporates a whole lot of lessons, international developments post Fukushima, right from IAEA publications, ICRP publications, the recommendations of ICRP publications. So this is holistically revised, updated requirements that was published in 2022. And the key areas, these are some of the key areas. That's the decision making, as I was mentioning all the way, and optimized protection strategy, emergency planning zones, response framework, and exercise methodology. So these are the key areas that are the key areas that will go into the revision or updation of this specific safety guide that is targeted for nuclear facilities. And we have followed an approach in updating these requirements, which we call a bottom to top approach, because when we publish this code in 2022, AERB took a very considerated approach that before publishing any revised requirements, we ensured that it is implementable. For that, we took a bottom to top approach, where we had in the early 2016, we had an elaborate review, and we went through all the developments, Fukushima, ICRP, all of this. I put this here for your reference. And based on this, we chalked out we decided to develop the technical basis. Okay, that actually goes into framing our guidelines and requirements. So the technical basis was developed, And we also did implement some of the changes, some of the new approaches that we are actually planning to put in the new requirements and the new framework. So these things we actually tested through interview instructions, feedback, and stakeholder consultation. I would say stakeholder consultation is on the key cornerstone in the revision of regulatory document process. And so this approach have helped us in ensuring that effectively managing the transition from the existing requirements and guidelines to a new set of updated requirements and guidelines. So that it also ensured that the necessary or expected preparedness or improvements changes by the licensee as well as by the local authorities are implemented, not waiting until we publish this, all these documents. So we ensure that these are timely, being adopted by the response agencies, and they are also implemented. So this is the way we went about. We went about with the revision of the regulations, and we are quite satisfied that necessary changes are timely done, and currently a satisfactory level of satisfactory framework and the level of preparedness is being maintained by the licensee as well as the response agencies. And let me just take you through the emergency preparedness oversight domain. And how AERB does the oversight part is that the oversight is strictly restricted to the licensee, and we do the oversight through the review and approval of EPR plans, that is emergency preparedness and response plans of the licensee. And we also conduct regulatory inspection programs specifically focused with special modules for emergency preparedness and response. And we conduct an elaborate observation and evaluation program towards the emergency exercises. So this is a key focus for AERB, and we believe that this is a key cornerstone that is going to ensure an effective preparedness level by all of the agencies. So these are the three domains that that we tools through which we do the oversight aspect. And I'll tell you that currently the licensees maintain the plant emergency preparedness plan, site emergency preparedness plan, and an offsite emergency preparedness plan. And as far as the offsite emergency preparedness plan is concerned, it is in two parts. That is part A, where it covers the responsibility of the licensee, because the licensee is responsible for advising the district authorities for notification of the notification for identifying, declaration, notification of an offsite emergency promptly, and also advising the district authorities, the local authorities, what are the likely protective actions that are to be taken based on the estimation of the current weather condition, the likely areas that are likely getting affected, and the level of release that is going to happen, if at all a release is going to happen, and what is all this, huh? Remove. Right. Okay, so these are the things. And then you also have offsite emergency preparedness plan maintained by the local authorities, covering the response actions to be taken in the public domain. And these plan, the offsite plan of the licensee is approved by reviewed and approved by ERB. The offsite plan for the district authority is maintained as part of the district disaster management plan, an integrated part of the district disaster management plan, and they are approved by relevant authorities, state and national authorities, and reviewed and approved by NDMA also. And AERB's review is also considered as part of the review and approval process of the district authorities plan. And as part of regulatory inspection program, the focus areas are communication facilities. We ensure that these facilities are in high state of readiness. During our inspections, we make specific focus on these areas. That the response facilities identified as the plant emergency control center, on-site emergency control center, and off-site facilities that are identified for any response depending upon the phases of emergency all of these facilities, the readiness of these facilities are inspected, and the emergency response procedures, are they maintained, and how are they updated, and the equipments available for on-site emergency response, and the training that training of manpower for emergency handling. And we also look into the improvements that are being implemented based on the periodic exercises. I will talk about the exercises program, what an NPP maintains in the next couple of slides, and computation tools, records, and how they are maintained. All of these areas are the focus areas that goes into as part of the regulatory inspection program of AERB. And when it comes to exercise, I will give you a brief overview of the emergency exercise performed at NPPs. And AERB doesn't have an elaborate observation and assessment program of emergency exercises. AERB officials observe the emergency exercises, all offset emergency exercises are witnessed and evaluated by AERB, and AERB also does the monitoring of these exercises from our own NREMC, that we call that Nuclear Eligible Emergency Monitoring Center, which actually helps in conducting or executing AERB's role during an emergency, which is majorly that overseeing licensees' response action, and advising other authorities if any need is there, and also informing public as and when necessary. So for these functions, we run an emergency response monitoring center, and this center is also used for monitoring the exercise program as well. And an overall assessment and evaluation is made based on the on-site observations and NRMC monitoring outcomes, and we do identify major key strengths and key areas for improvement. And these areas are identified, and a systematic follow-up program is maintained to ensure these identified gap areas are attended through a corrective action program by the licensee. And the exercise reports and corrective action recommendations are processed in AERB through established AERB review and assessment processes. And the various type of emergency exercises conducted by the licensees are plant emergency exercise, site emergency exercise, and offsite emergency exercise. The frequencies for plant and site emergency exercise is plant emergency. They are conducted once in 3 months, and site emergency exercises they are conducted once in a year. And when it comes to offsite emergency exercise, it's a whole new program now. It consists of 3 type of exercises. So it consists of 3 type of exercises. So this is in deviation from the past that we used to conduct one exercise as a one-stop solution for a host of exercise objectives to be met. And now we have put a scheme where it includes a modular exercises and integrated exercises, and where the response agencies can conduct the exercises in a modular fashion in order to achieve a certain identified exercise objectives. And you also conduct an integrated exercise where all the response agencies are participating at one go, and specific response functions, command control functions, early warning, field response, communications, coordinations, all of this are tested on a realistic basis. So this is an important aspect I would like to mention, that these exercises are conducted under a realistic condition. That is, the scenarios for these exercises are not known for any of these organizations or the response facilities, or for the matter the licensee or the response facility. What is the accident condition chosen for the exercise? What is the likely villages that are going to be that early warning systems are to be activated, or early warning teams has to be sent to these villages. So none of this is information is available a prior to these participating agencies. They are introduced through injects. The total scenario is unfolded in form of number of injects during the course of the exercise duration. The exercise duration runs from close to 4 to 6 hours, depending upon the type of exercises. And the exercise scenario is actually unfolded through use of injects. and the response of all these response agencies are tested under realistic condition. The pattern, the weather condition, the actual weather condition during the exercise are to be estimated or to be used for the response action, and it will also call for a predicted weather condition also to check the overall functions as well. So this is a key highlight of this Q exercise methodology. And before getting into this new framework, we did an elaborate mapping exercise, where we identified that what are the actual objectives of an exercise, and currently what are the gap areas. We actually did a mapping for the existing, the old pre-2018 exercise format. And we went through an assessment where we identified key gaps, and we chalked out a strategy or a scheme, which of the objectives can be addressed or tested in what sort of an exercise. So either a modular or a integrated exercise, and who are the agencies that is going to lead, or target agencies, who will be target agencies. So we chalked out a scheme and plan, and each of this exercise has its own scope. When we call a tabletop exercise, it is actually purely on decision making. Okay, Sunny, do I have 5 more minutes? Right. Okay. So each of these exercise has its own objectives. Especially when I talk about tabletop exercise, it is about identification, classification, declaration of emergencies, and the capability of the licensee to estimate source term, which I was talking about as part of as an important aspect, and the capability to take actions to incorporate prevailing weather conditions and plant conditions, and identifying the affected area and the magnitude of consequence using dispersion and dose calculations, and the use of decision support system and protective action recommendation to district authority. So this is so relevant to the topic that I think you can relate to the topic that I was discussing in my first part of the lecture. That is the dispersion and decision support system. So there are certain response functions licensee has to execute as part of their responsibility in handling offsite emergencies. So the complete focus is on this very focused exercise, and we challenge the ticensee or the response organization using realistic conditions, and we ensure that they are well prepared to handle any eventual accidents. Okay. So the next part is scope of ICCR exercise, that is integrated command control exercise. This also checks both decision making as well as the command control functions. And apart from the decision making, that is decision making, I would say identification, declaration, notification of emergencies. Apart from those aspects, it also checks about the activation of various response centers. The response centers, I would make one in the facility side, one in the district authority side, and one in the national side. So all of these response functions are activated, and the coordinated response from all of the response agencies are checked for the complete course of emergency phase. That is both early phase and intermediate phase until the termination of the emergency is there. Whoever agencies are responsible for handling these emergencies are part of this integrated command control response exercises, and these are witnessed, and oversight is being done both by AERB and NDMA. And field response for early response is done. That is, district authority do early field response for sending teams. How many teams to be sent for early response, for sending distributing ITB, and doing traffic control. These are the very critical functions that we do in the early phase of an emergency. So we check the district authority's responsibility, district authority's capability to respond to a unknown scenario for under realistic condition. And I would say both the licensee and the district authorities are very well tuned to based on the exercises which we have conducted. The response framework is very satisfactory. Response framework is satisfactory, but exercises have always identified a lot of gap areas, and those gap areas continue to get addressed, and our level of preparedness is getting continuously improved. Okay, so that is what I just want to convey at this moment. And the scope of the FED exercise, that is field exercise and demonstration, this is solely focusing on the field demonstrations, basically to take decontamination. How do you do a decontamination? How do you set up a medical kind of screening and contamination post? And the coordination between specialist teams, the civil defense and police teams working together, and use of personal protective equipments, and those monitoring procedures, and the focus is also that we do exercises at the areas, local areas, that is the district authority conducts these exercises at the villages or the areas that are affected in accordance to the type of protective actions that are likely to happen. By this, I mean that no district authority will not be testing evacuation in an area 5 to 6 kilometers away from the plant or facility, because the evacuation is not necessary far away from the plant. To that matter, for the small reactors, the 220 megawatt type of reactors, that is, the evacuation itself is not necessary. Simple protective actions like iodine thyroid blocking, staying indoors, will ensure that public are not getting any doses more than the planned, or more than the reference levels. Okay, so such things that are focused. The field exercise is focused in accordance to the hazard of the facility. What are the likely protective actions that are going to be necessary in case of an emergency in the public domain? So the overall, the framework looks this way. That is, each of this, all this type of emergency exercises are listed here. And you see the response agencies for tabletop is identified, target response agency, NPP. And for field exercise and demonstration, it is district authority. And for integrated command control exercise, that is NPP. There's also the national agency, that is CMGDAE and RERD. These are technical response agencies by the DAE and also district authorities. So all of them participate together in the integrated command control exercises. And the frequency of these exercises are again different. For tabletop, you have every 2 years for every station, not just a site. Every station, NPP station, every line, a site may have 4 stations, 2 stations. Irrespective of the number of the sites have, each of the stations have to conduct the tabletop exercise, because our focus is on the licensee's management's capability to advise protective action in response to the type of the facility. So AERB has hugely emphasizes on the capabilities of licensees in this context, and these exercises are conducted every 2 years. For example, for a given site, Rajasthan site, every 6 months this exercise will be happening. Okay, every 6 months this exercise will be happening. And you see the field exercise and demonstration is conducted by the district authorities, and the plan is to conduct cover all the areas, all the likely affected areas over a period of 8 years. And every year the district authority will be conducting the exercise in a specific identified location across around the facility. And the district authority is the responsible agency, and the planning is being supported by NPP for technical inputs, because the facility will only be able to give what are the likely protective actions that will be necessary at this distance. Okay, so that will depend upon the hazard level of the facility. So this input is necessary, and for that the NPP is going to support the planning of these exercises through giving the technical inputs, and the oversight agency is NDMA. And as for the integrated exercises, emergency exercises concerned, the frequency is every 3 years, and you have the responsible agency, prime responsible agency is NPP and district authority, and both AERB and NDMA will be the oversight agency. And you see two not modular exercises and one integrated exercise. Okay, so it is a very comprehensive exercise framework covering all the exercise objectives over a specified period of time, and through which we believe that this exercise program or exercise scheme is going to hold us in good stead as part of our preparedness. And I've discussed the highlights across the emergency, highlights of the exercise methodologies, as I was discussing the type of exercises and the scope of these exercises. As I said, the point is it is conducted under a realistic scenario, okay, and it is given through injects. The scenario development finalization by AERV expert group and include meltdown release conditions. Although these are practically eliminated conditions, but still we insist that you get prepared or you should be prepared for all these conditions. And the classification set by plant emergency action levels during the early phase. And the objective is to check the response timelines for declaration, activation, and field response. So we not just see that how they are responding, we check the response timelines. Okay, now AERB is giving guidelines for the expected response timeline for each of the responses for each of the response agencies. So we also check whether the response agencies are able to conduct the response in that expected timeline objective. And we check the license between on-site and off-site facilities, coordination between plant and district authorities with respect to public information. This is one of the key areas of emergency management, and comprehensive assessment and corrective action mechanism. This exercise program also not just conducting exercise and leaving off. It follows up with a comprehensive exercise and assessment mechanism, and issues related to CM interface between the coordination agencies between CMG, interface and coordination between various response agencies is actually dealt with DAE, CMG DAE. If at all there is a finding that says that the coordination between these two agencies needs to be attended for this particular aspect. So if such things are discussed, and then corrective action mechanism is implemented through DAE-CMG. So this is the overall program that is existing for as part of oversight program. And I would just leave you conclude this lecture by just also telling that there are challenges ahead, especially in the post-accident management. That is field monitoring and survey. Quick, elaborate field monitoring and survey capability exist, and our continual improvement in that aspect is important. And the public dose estimation and actual assessment of actual consequences is a thing that will be necessary, because the source term estimation for the actual estimation of consequences is critical. And the termination and stakeholder consultation, that while we are terminating an emergency, you need to have stakeholders on board, and what are the conditions, because emergency termination would have its own challenges, and probably a few protective actions may have to be continued, but then without any much intervention in public life, and cleaning and decontamination aspects, because these things that we don't test ourselves every day, and an emergency condition can throw you new challenges, and the resilience that our program has, or that we are inbuilding the aspect in our program, that way that we are going to inbuild in our program, the resilience is a key aspect in challenging these post-accident management aspects. And I would like to just conclude my talk here. And if you have any questions on both parts, that is the dispersion and modeling DSS part, and as well as on the regulatory oversight part, I would be happy to respond to. Thank you. I think there are no questions. I believe that I have conveyed the message clearly. And if you still have questions, you can get in touch with me. and I would be happy to respond and clear your doubts. Thank you.